Now in this video we will be discussing about the interrupts which are used in 8085. Now this interrupt is a process of data transfer where the external devices or the peripheral devices informs the processor that it is in need of the communication and request its attention, the attention of the processor. Now of course this process is initiated by the external devices, and it is a asynchronous data transfer scheme. It comes under the meaning thereby at any time the peripheral can initiate the process without the reference of the system clock. So however the request which has been sent by the peripheral device can be directed to be controlled by the processor itself. Now the microprocessor requests are classified into two parts. One is the interrupt requests are classified in two parts. One is maskable and another is a non-maskable. The microprocessor 8085 is concerned, it includes 4 maskable interrupts and 1 non-maskable interrupts. Among the 4 maskable interrupts, one is vectored, which requires external hardware to supply the call location to restart the execution. Now whenever it is I am talking about the call location, it is the call location where certain program has been written, subprogram is written, and the content of that program is such manner that the device which has interrupted the processor will be able to transfer the data. So actually the content of the subprogram or the subroutine is to transfer the actual data. So besides that, 3 are the vectored, and every vectored interrupt has its specified location that will be coming, that what will be the different location on which the call transfer is to take place. Now the microprocessor can ignore or delay the maskable interrupts. It is performing some critical tasks. So however it may respond the non-maskable interrupts not immediately, after some time. In many ways the maskable interrupts is like you can take an analogy of a telephone which can be kept in a hook, and you can it is ringing, and so if whenever you are interested, if you are doing something, whenever you are interested, you are going to take the message. But non-maskable interrupt is a kind of an interrupt which has to be handled immediately whenever it is being received by the processor. It cannot be avoided. So meaning thereby the maskable interrupts are those interrupts which can be avoided for a certain time, but non-maskable interrupts are those interrupts which cannot be avoided for a certain time. Now this interrupt process allows the microprocessor to respond the external request for on the demand basis by executing the service routine. So microprocessor, whatever it will be doing, it will be completing its current instruction, and then it will be switching the control will be switched to the subprogram which is meant for the actual data transfer process. So interrupt delayed data transfer is in which when the input output device is ready to send through the interrupt line. So whatever MUPI is doing, it will be first completing its job, and the content of the program counter, which is the next instruction address, it will be stored in the stack, and it will be going to take the ISS. ISS stands for interrupt service subroutine. Interrupt service subroutine is already made by the manufacturer, and it is stored at a certain memory location. So whenever request has been granted by the processor, it stops its normal execution and executes the service subroutine related to that particular line through which the peripheral has interrupted. So this is different from as far as the pooling process is concerned, in which the MUPI time is going to be wasted while keep on checking that whether device is ready to transfer the data or not, and MUPI is not wasting its time in this particular case. MUPI is doing its job. Whenever it is receiving any kind of interrupt, then it is going to handle that particular peripheral devices. Now, it may be possible that there are many devices which are attached to the processor. So, many devices are going to interrupt at the same time. So, it may be the case in 8085. So, there are three possibilities that there are single line through which the microprocessor can be interrupted. There may be multiple lines. So, if there is single line and many devices are attached, that is also called multiple interrupt. If there are multiple lines and each devices are attached to the each line, that is also an example of multiple interrupt. And there are many lines and many devices are connected to each line, that is also an example of a multiple interrupts. When several input output devices are connected to a particular line, of course, there will be some logic circuit, that is OR circuit, through which it will be connected. So, if there are single line on which the many devices are connected, and if any one of the device has interrupted, so microprocessor, what it has to do, it has to pull that which device, it will keep on checking that which out of many devices connected to that particular line, which device has interrupted. So, if more than one device has interrupted at a time, so the microprocessor has to set a priority, and then it pulls on that priority. Suppose there are 4 devices which are connected with the single line, and the first device is having highest priority. So, it will first check whether first device has interrupted or not, then it will check the second and third, and then so this particular scheme is little bit slow because it is using pooling process, and this pooling process can also be done with the help of software as well as the hardware. But if one device is connected to each line, so any device which is connected to the line and that device is going to interrupt the process of the microprocessor, there is no need of pooling. Immediately the processor came to know that this line, through this line the device has interrupted. So, concerning to that line, there will be a certain subroutine program that will be executed automatically by the microprocessor. So, such type of interrupt scheme is known as vectored interrupt. But if there is a possibility that there are more devices which are connected to each level, then in that particular case, it has to take the process of pooling as well as vectored interrupt. Both the schemes will be used, because if there are many devices and many lines and one line through which many devices can interrupt, so it has to check that which device has interrupted, and depending upon that particular line through which the peripheral devices have interrupted, it has to go to the vectored address. Now, this diagram is a total representing the interrupts used in 8085. We already know that there are 5 lines which are available in 8085, a trap 7.5, 5.5, 6.5 as well as the INTR. Now, as you see, whenever any device who has interrupted with the trap, it will go to the address 0024. Any device who has interrupted through RST 7.5, it will go to the address 003C. These are the addresses where of the call location where the subroutine subprogram is written. So, if any device is interrupted through RST 7.5, it has to execute the program which is written on 003C, and the program which is written on 003C is the actual program which is able to transfer the data. Similarly, for 6.5 we have an address 0034. For 5.5 we have an address 002C, and if it is INTR line can be used along with the RST instructions, because whenever any device who has interrupted through INTR line, still it needs RST code, and we have already gone through the subroutine. Whenever we were discussing subroutine, we have also told you that there are 8 RST instructions. The RST stands for restart instruction, and these RST codes have different sub call address. So, if it is RST 0, it will move to 0000. For every RST instruction, there is a separate address which is assigned to that. So, in case of RST 5.5, 6.5, 7.5 and trap, we have a separate address, but whenever any device wants to interrupt through INTR line, it also needs RST instruction to be included in the program, and accordingly it moves to that particular address. So, as far as when we are going to summarize the interrupt of 8085, it has 5 interrupt lines, and these interrupt lines can be enabled because any device who want to transfer the data through the interrupt by the interrupt process, it is necessary that the 8085 has internally available interrupt flip-flop that has to be enabled. Until unless if it is not enabled, then any kind of vectored interrupt or any kind of maskable interrupts cannot be interrupted. Of course, non-maskable interrupts are exceptional of that. So, it is necessary that any device who wants to transfer the data through the interrupt enable flip flop must be enabled before that. So, for that particular case 8085 uses an instruction, that is EI instruction. EI stands for enable interrupt. What it does, it enables the flip flop. By enabling the flip flop, interrupt enable flip flop, it is going to inform the processor that any device which is connected with any one of the interrupt line, if they are going to interrupt and want to transfer the data, then it is allowed. Similarly, we also have an instruction called disable interrupt, that is DI instruction. All these instructions are single byte instruction, which the purpose of using DI instruction is to disable the interrupt enable flip flop. So, any device who wants to transfer the data, and if the interrupt enable flip flop is disabled, it cannot be entertained by the processor. So, when interrupt is received, processor completes its instruction, current instruction whatever it is executing, and resets the enable flip flop and takes on the ISS. So, the other devices are not able to interrupt. Whenever it is entertaining one interrupt, then all the rest of the interrupts are being resets, because whenever it is entertaining one of the interrupt, it is not allowed to interrupt again the processor. So, similarly, we can also do the masking process. Whenever one interrupt is being entertained, then we can also mask the other interrupts, so that rest of the peripheral devices which are connected to other interrupt line cannot be interrupted. Now, let us see what is the maskable interrupt and the non-maskable interrupt. Maskable interrupts are those interrupts which can be avoided for some time, and non-maskables are those interrupts which cannot be avoided. Now, trap is a non-maskable and the rest of the interrupts are maskable interrupts. Non-maskable interrupts are used in the emergency situation, and rest of the interrupts can be used for any kind of data transfer process. Now, how this masking is being done? This can be available by the help of a program, by writing a program or using a certain instruction which allows to mask the certain interrupt lines. Now, as far as there are two kinds of interrupt, one is hardware interrupt and the another is software interrupt. Hardware interrupt are those interrupts which if the interrupt is caused by a hardware device, that is called hardware interrupt, meaning there by any line through which the processor is being interrupted, that is a hardware interrupt. But the interruption of the program can also be done. Interruption of the process of the processor can also be done with the help of instruction, and that instruction is RST instruction. So, that kind of interrupt is called software interrupt. So, the instructions which are used for the interrupts are, as I told you, EI and DI. Now, in the case of EI, it is a single byte instruction. It enables the interrupt process, and again it is written it is going to disable the interrupt process. Now, both the things are contradictory to each other, but the meaning is very simple. Once it enables the interrupt process and one of the device has interrupted the microprocessor, then what it does, it disables the rest of the interruption. So, that is why EI stands for enables as well as disable. Once a process is enabled, once interrupt process is enabled, it is going to disable. You can compare this instruction which is going to enable as well as disable by a simple instruction, by a simple analogy. You will be using a lot of programming skill, and you will be using to stop the program, to end the program by using a stop instruction and the end instruction. Now, a stop instruction is a kind of instruction which temporarily halts the program, and end instruction is a kind of instruction which is going to temporarily permanently stop the execution. Now, this is the difference. Whatever is the difference between stop and end, the same difference lies with EI and DI. Whenever we are using EI, it is enabling the interrupt process as well as it is disabling rest of the interrupt process. And whenever you are using DI, it is going to disable all the interrupt process besides the non-maskable interrupts. So, EI is a simple kind of stop and DI is a simple kind of end instruction. So, whenever DI will be used, it will disable all the interrupts. Now, as far as the RST instruction, we have already discussed this RST instruction in the subroutine. We have 8 call locations at which the restart instruction can be executed, and this is kind of a software. interrupt. So, RST-N is the code template or the format of writing RST instruction, RST 0, 1, where N varies from 0 to 7, and each instruction has its own hex code, and respect to the each instruction there is a certain call location where the subprogram is written. Now, as far as the interrupt call location is concerned, and we are talking about the maskable and the non-maskable interrupts. Trap comes under the category of the non-maskable, and the rest of the interrupts are under the category of the maskable. Similar to RST instruction, we have an address code for the RST 7.5, 6.5 and 5.5, that is 00C, 002C, 0034, 003C, 0024. These are the call location for executing the subroutine subprogram related to the interrupt. Now, as far as the RST 6.5, 7.5 and 5.5, these are the maskable interrupts, and it is being enabled by the instruction EI, as well as it uses set interrupt. Another instruction is used to check the status whether which interrupt line is masked or which interrupt line is not masked by using a simple instruction set interrupt mask, that is SIM. Now, the execution of SIM enables or disables the interrupt according to the bit pattern of the accumulator. So, we have to load certain value in the accumulator, and what SIM instruction used to do, it used to read the content of the accumulator and then decides and informs the microprocessor that which interrupt line is masked and which interrupt line is available, and DI instruction simply disables the interrupt. So, let us now discuss the SIM instruction. The SIM instruction is a single byte instruction, and this instruction reads the content of the accumulator and it enables or disables the interrupt depending upon the availability of the bit pattern in the accumulator. So, before executing the SIM instruction, what we have to do, we have to put certain values into the accumulator, and whenever we are using SIM instruction, then SIM instruction, what this will do, it will read the content of the accumulator and then informs the processor that which interrupt is masked and which interrupt is not masked. Now, as for the format of the SIM instruction, it depends upon the value which has been put on the accumulator, and you know accumulator can accommodate 8-bit number. Out of this 8-bit number, right from D0 to D7, D6 and D7 is used for the serial input output data transfer, and it has no effect on the interrupt process. But as far as the rest of the bits are concerned, D3 bit में लिखा हुआ है MSE. MSE stands for mask set enable. It allows to enable the masking process of the individual interrupts. So, as far as logic 0, if it is logic 0, it means enables the corresponding interrupt, and if it is logic 1, it disables the interrupt. Now, as far as the D4 is concerned, D5 remains unused. D4 is concerned, D4 is an additional control for the RST 7.5, and if it is 1, it means RST 7.5 is reset. Otherwise, if it is 0, RST 7.5 is available. Now, as far as D0, D1 and D2 is concerned, this informs the availability. If D0, D1, D2 is 0, 0, 0, it means all these interrupts are available, and if any one of these or all of these are 1, it means these are masked. So, 0 stands for available and 1 stands for masked while executing the SIM instruction. Now, the entire interrupt process, the disabling process Now, the entire interrupt process can be disabled by resetting the interrupt enable flip flop by using these 3 instructions, by using EDI, or if we put the system reset, or if any interrupt is recognized, it is automatically reset. Now, as far as the programming is concerned, if we have to enable all the interrupts of 8085, so for that particular purpose, we have to use enable interrupt line, whose process is to enable all the interrupts, and then we have to put certain pattern into the accumulator, so that whenever we are using sim instruction, we are able to enable the individual interrupts. So what we are doing, we are putting 08 into the accumulator. Whenever we are doing 08 into the accumulator, 08 means D3 bit is 1 and the rest of the bit is 0. So when rest of the bit is 0, what it stands, and D3 bit is 1, D3 bit is 1, it means mask set enable flip flop is enabled, and 5.5, 6.5 and 7.5 is 0, it means these are available. 7.5 is 0, it means it is also available, and D5 is not used, so whether it is 0 or 1, it hardly matters, since it is not concerned with the serial input output. So all these two will be 0. So if we want to enable all the interrupts, what we will doing, we will be putting 08 into the accumulator. Now, as far as the enabling of the next process is to enable 6.5 and disable 7.5. So we have to put certain values into the in the form of a bit pattern into the accumulator, so that 6.5 will be enabled and the 5.5 and 7.5 is disabled. So to make 5.5 and 7.5 disable, we make D0 is equal to 1, D2 is equal to 1, as well as MSE, because we want to mask set enable, it should be 1. So the lower nibble will be 1, 1, 0, 1, and 6.5 has to be available, so D1 will be 0. So 1, 1, 0, 1 is equal to 8 4 12, and that is will be 13, and 7.5 has to be made available. If 7.5 has to reset, so for that particular purpose we have to put RST 7.5, that is D4 bit as 1 and the rest of bit 0. So whenever we are doing this, we are getting 1D, and what this 1D has been put into the accumulator, and whenever it is put into the accumulator and then sim instruction is executed, it is going to enable the RST 6.5 and it is going to disable the RST 7.5 and 5.5.